Alright, so I want to work a couple of practice problems using Newton's second law. This will be a good review for those of you who are in class, and for those of you who had to be out, this will get you caught up. So I want to first of all take just a scenario of a ball, and let's give it a mass of 3 kilograms, and we're going to suspend it from a rope or a chain. And at first we're going to have it be moving down at a constant rate of 5 meters per second. And then the question I want to ask is, what's the tension in the chain as it moves this way? And so the first thing I'm going to do is I'm going to draw a diagram. I'm going to draw a picture and then draw a free body diagram. And on this free body diagram, I'm going to, of course, label all the real forces acting on the ball. In this case, there's, of course, mg, which is directed towards the center of planet Earth, which normal people call down. And there's also this opposing force that is in the upward direction that we're going to call capital T for tension. And that's the tension in the rope or chain, which is, of course, what we're looking for. Now, one of the first things I want to do is assign a positive direction. And you could make an argument for either up or down to be positive in this case. You could say, well, it's moving down, and so I want down to be positive. But the reality is, as I've mentioned, rule 1 is that I'm going to make acceleration along an axis and positive if possible. But in this case, it's moving down with a constant speed, and so we're going to show here in a minute that there is no acceleration, and so it's completely irrelevant which direction I choose as positive. And so I'm going to choose down as positive, but of course that's not going to change ultimately my final answer. But if I say that down is positive, then I'm ready to write an F-net statement. And so I want to write a statement that describes all the real forces acting on the ball in this case. And since I said down is positive, then that means that mg is in the positive direction, and so I'm going to list it first as I list my real forces acting. And then there are no other positive forces acting, and so I move on to the negative ones. And of course tension is in the opposite direction. It's in the up direction, which I've assigned as negative, and so I assign it a value of negative. And so there's my F-net statement, that the net forces acting on the ball are mg down and tension up, and there are no other forces acting. So now, according to Newton's second law, F-net always equals ma, so I'm going to substitute for that. And that equals mg minus t. And then, as I mentioned just a second ago, it's moving down at a constant rate of 5 meters per second. And so, well, what's the acceleration? 0. And so if the acceleration is 0, then the forces acting are balanced, the net force is 0, and that shows me that T simply equals mg. Well, now that I have my unknown isolated, I'm going to substitute the known values, and so the mass is 3 kilograms, gravitational field strength near the surface of planet Earth is 10, and therefore mg is 30 newtons. So the tension in the rope is 30 newtons. And again, that is completely counterintuitive, that the tension in the rope is the exact same when it's moving down at a constant speed as if it were not moving at all and were remaining perfectly still. If I had an example where the ball was at rest, hanging from the chain, then the tension in the rope would be opposing gravity equally as well, and so it would be a tension of 30 newtons that way as well. But again, this is that notion of Newton's first law that's so surprising. Once the ball starts moving down, it wants to continue moving down, and the only force I have to apply is enough to keep gravity from speeding it up, to keep it moving at a constant speed. And so again, moving up at a constant speed, moving down at a constant speed, or not moving are all the exact same thing in terms of what the net force is acting on them, because the acceleration is 0 and therefore the net force is 0. All right, so let me work a second example. We'll keep that same 3 kilogram ball still suspended by a rope or chain. But this time, I want to know if the tension, let's say that we know that the tension is 40 newtons, then what is the acceleration? How would we describe the acceleration of the ball if we know that the tension is 40 newtons? Well, I'm going to take the exact same approach again. I'm going to draw a free body diagram and label the actual forces acting on the object. Of course, there's mg in the down direction. There's still the tension in the rope. And I'm going to go ahead and take a peek at this. 40 newtons, how does that compare to mg? Well, mg near the surface of Earth for a 3 kilogram ball is going to be about 30 newtons. And so I'm going to make tension pronouncedly longer than mg. What that's going to help me anticipate and remind me then is which direction should I choose as positive? Well, Rule 1 says if there's an acceleration, make it along an axis and positive if possible. And so I know that the net force, the total force, is going to be up because the up force is greater than the down force. And so for that reason, I'm going to choose up as positive. Now I could work it with down as positive and I'd still get the same answer, but this is the most straightforward and the easiest way to guarantee I don't make silly mistakes. All right, so now I'm ready to write an F-net statement again. And since I've chosen up as positive, it's going to look slightly different this time. Tension is going to be listed first in positive, and mg is in the negative direction, and so F-net equals T minus mg. Well, what does F-net equal? F-net equals ma, so I'm going to substitute that. T minus mg, and then I'm looking for acceleration, so I'm going to isolate acceleration by dividing both sides by the mass. So T minus mg, that whole quantity divided by the mass will give me the acceleration rate. Well, now I've got my unknown isolated, and so I'm ready to substitute. I've given that tension is 40, m is 3, the gravitational field strength near the surface of planet Earth is 10, all over the mass of 3. Well, that's simply 40 minus 30 is 10 over 3. 10 thirds, of course, is 3.3 meters per second squared. And of course, I need to be careful and give a direction. And of course, the direction in this case, I got a positive value. I've assigned up as positive, and so the acceleration is up. Now notice, I have solved for what the acceleration of the ball is, but that doesn't tell me anything about the motion of the ball. In other words, is this ball moving up or moving down? Well, it's not enough information is given to know. If it's moving down with an upward acceleration, that would simply mean that it's slowing down. But if it's moving up with an upward acceleration, that means it's speeding up in the up direction. So again, as we've seen with our kinematics graphs, from the acceleration we can tell how the velocity is changing, but we can't necessarily say anything about how it's actually moving. And so the acceleration is up, and so it's either speeding up in the up direction or slowing down in the down direction, but we have a magnitude of 3.3 meters per second squared up, and so therefore the acceleration is up. And notice again that the net force is in the same direction as the acceleration. There's a greater upward force than a downward force, and so the acceleration is in the upward direction. And that is consistent with this previous problem, right, where the two forces were equal. I've got a greater tension this time than I had previously, and so I have an acceleration up where before I had an acceleration of 0.